In November 1857, 10,000 spectators gathered on the banks of the Thames to witness the launch of the largest ship ever built. The vessel measured 692 feet in length, weighed over 18,000 tons, and dwarfed every other ship afloat. Its designer, Isambard Kingdom Brunel, had promised a launch that would demonstrate British engineering supremacy to the world. Instead, the ship remained immobile, stuck on its slipway, despite every effort to move it. Hydraulic rams strained and failed. Chains snapped under the load. 3 workers died in the chaos, crushed by equipment or falling debris. The press, invited to witness triumph, reported humiliation. Critics who had called Brunel a megalomaniac now saw confirmation. His response was to ignore them and fix the problem. Over the next 3 months, Brunel worked obsessively to free the ship, spending his own money to hire equipment and engineers. On January 31, 1858, the SS Great Eastern finally entered the water, but by then the damage to Brunel's reputation was done. The press mocked him. Investors grew nervous. His health, already fragile, deteriorated under the stress. Yet Brunel never doubted the ship's potential. The Great Eastern was designed to carry 4,000 passengers non-stop from Britain to Australia without refueling, a feat no other vessel could accomplish. Its double hull and watertight compartments made it the safest ship afloat. Its twin propulsion systems, screw propeller and paddle wheels, ensured reliability. Brunel had calculated every detail, and the calculations were sound. The world simply wasn't ready for it. Isambard Kingdom Brunel was born on April 9, 1806, in Portsmouth, England, the son of Sir Mark Isambard Brunel, a distinguished French-born engineer who had fled the French Revolution and settled in Britain. Mark Brunel was already famous for his innovative block-making machinery used by the Royal Navy, and young Isambard grew up surrounded by engineering drawings, mechanical models, and discussions of stress, force, and materials. His father recognized his talent early and sent him to France for education, first to the College of Caen in Normandy, then to the prestigious Lycée Henri IV in Paris, where he studied mathematics, drawing, and engineering under some of Europe's finest instructors. By age 14, Brunel was fluent in technical drawing and could calculate structural loads with precision. In 1822, at age 16, Brunel returned to England and began working with his father on the Thames Tunnel, an audacious project to dig a passage beneath the river, connecting Rotherhithe and Wapping. No one had successfully tunneled under a major river before, and most engineers considered it impossible. The soft riverbed mud would collapse, flooding any excavation before it could be completed. Mark Brunel had invented a tunneling shield, a massive iron framework that protected workers as they dug. But the project was dangerous. In 1827, the tunnel flooded. Isambard, then 20 years old and serving as resident engineer, was nearly killed, dragged unconscious from the water by rescuers. He spent months recovering in Clifton, near Bristol, where the fresh air and countryside helped restore his strength. While convalescing, Brunel learned of a competition to design a bridge spanning the Avon Gorge in Bristol, a dramatic chasm over 700 feet wide and 250 feet above the river. The competition attracted entries from Britain's leading engineers, including Thomas Telford, the most respected bridge builder of the era. Brunel, just 23 years old and recovering from near death, submitted a design for a suspension bridge with Egyptian-inspired towers and a single span of wrought iron chains. Telford dismissed it as impractical and proposed his own design with multiple supports. The judges, torn between Telford's reputation and Brunel's vision, eventually chose Brunel. It was his first major commission, and it established him as an engineer willing to challenge convention. Construction of the Clifton Suspension Bridge began in 1831, but funding ran out after the towers were completed in 1843. For 16 years, the unfinished structure stood as a monument to unfulfilled ambition. Brunel moved on to other projects, and the bridge seemed destined to remain incomplete. Brunel never saw it finished. After his death in 1859, fellow engineers completed the bridge as a memorial to him, using chains salvaged from another of his projects. When it opened in 1864, the Clifton Suspension Bridge became an icon of Victorian engineering, carrying traffic across the gorge to this day. It remains one of Bristol's most recognizable landmarks, a testament to Brunel's vision and the determination of those who completed it. In 1833, Brunel was appointed chief engineer of the Great Western Railway, a proposed line connecting London and Bristol. The project was controversial. Critics argued that such a long railway over 116 miles was economically unfeasible and, technically, impossible. Existing locomotives lacked the power to climb steep gradients, and railway construction was still in its infancy. Brunel ignored the skeptics. He surveyed the route personally, spending months walking the terrain, measuring gradients and calculating the optimal path. His design avoided steep inclines through a network of cuttings, embankments, viaducts, and tunnels. The railway would be as level as possible, allowing trains to maintain high speeds with minimal fuel consumption. Brunel made a decision that would haunt him for decades. He chose a broad gauge of 7 feet, wider than the standard gauge of 4 feet 8.5 inches used by most railways. His reasoning was sound. Broader gauge allowed larger, more powerful locomotives, smoother rides, and higher speeds. Tests confirmed that broad gauge trains were faster and more comfortable than standard gauge, but Brunel's choice created incompatibility. Trains running on the Great Western Railway couldn't use tracks built by other companies, and passengers traveling between different rail networks had to change trains at junctions. Critics condemned the decision as arrogant and impractical. Parliament eventually mandated standard gauge for all new railways. Brunel's broad gauge, technically superior, was doomed by the need for standardization. The Great Western Railway's construction required feats of engineering that seemed impossible. Between Bath and Bristol, Brunel faced Box Hill, a massive limestone ridge that blocked the route. Rather than divert the railway, Brunel decided to tunnel through it. The Box Tunnel would be nearly 2 miles long, the longest railway tunnel in the world at that time. Critics declared it unsafe, predicting collapses and suffocation. Brunel calculated the ventilation requirements, designed the tunnel's arch structure to distribute stress evenly, and hired over 4,000 workers to excavate the rock. The work took nearly 5 years. Workers used 1 ton of gunpowder per week and 1 ton of candles for illumination. Over 100 workers died in accidents. When the Box Tunnel opened in 1841, it was celebrated as a triumph of Victorian engineering. Trains passed through smoothly, and the ventilation system worked perfectly. Brunel had proven that long tunnels were not only possible, but practical. The Great Western Railway reached Bristol in 1841, and Brunel continued expanding the network, eventually overseeing the construction of over 1,200 miles of track. His railways featured innovative bridges, viaducts, and station designs. Paddington Station in London, designed by Brunel with elaborate iron and glass roofing, became a symbol of modernity. Despite the controversy over broad gauge, Brunel's railways were faster, more comfortable, and more reliable than their competitors. In 1834, during a meeting of the Great Western Railway Board of Directors, someone remarked that the proposed railway was the longest line ever built. Brunel, never one to think small, reportedly replied, "Why not make it longer and have a steamboat go from Bristol to New York and call it the Great Western?" The board, accustomed to Brunel's audacious proposals, took him seriously. No steamship had yet crossed the Atlantic reliably using steam power alone. Ships carried sails as backup because their coal supplies ran out before reaching the destination. Brunel calculated that a sufficiently large ship could carry enough coal to cross the Atlantic with reserves remaining. He founded the Great Western Steamship Company and began designing the SS Great Western. The SS Great Western, launched in 1837, was a wooden paddle-wheel steamer measuring 236 feet in length. Brunel designed her to carry enough coal for the transatlantic voyage, with a third remaining as reserve. In April 1838, she raced against the Sirius, a smaller steamer that had left 4 days earlier. The Great Western arrived in New York only 1 day behind, with coal to spare. Proving that transatlantic steam service was viable, the ship entered regular service between Bristol and New York, making 64 crossings and establishing Brunel's reputation as a shipbuilder. She was the first ship to hold the Blue Ribbon, the informal award for the fastest Atlantic crossing. Brunel's calculations had been vindicated. Brunel's next ship, the SS Great Briton, was even more revolutionary. Launched in 1843, she was the first ocean-going vessel built entirely of iron, powered by a screw propeller instead of paddle wheels, and measuring 322 feet in length. Every major innovation in shipbuilding that would define the next century was present in the Great Britain. Metal hull, construction, propeller, propulsion, and watertight compartments. Brunel had tested propeller efficiency aboard the experimental ship Archimedes and concluded that propellers were more efficient than paddle wheels, especially in rough seas. The Great Britain made her maiden voyage from Liverpool to New York in August 1845, proving that iron ships driven by propellers were practical for ocean travel. She's now fully restored and open to the public in Bristol. The Great Britain's success convinced Brunel that even larger ships were feasible. In the early 1850s, he began designing the SS Great Eastern, a vessel so large it would dwarf every other ship afloat. Brunel's vision was a ship capable of carrying 4,000 passengers from Britain to Australia without refueling, a voyage of over 12,000 miles. No coaling stations existed along the route, so the ship had to carry sufficient fuel for the entire journey. Brunel calculated that a ship 692 feet long with a displacement of 32,000 tons could accomplish this. The design incorporated double hulls for safety, watertight compartments to prevent flooding, and both paddle wheels and screw propellers for redundancy. It was the most ambitious ship ever conceived. The Great Eastern's construction was plagued by problems. The shipyard, Russell and Company, underestimated the complexity and ran out of money. Brunel poured his own funds into the project, mortgaging his reputation to keep work moving. The launch in 1857 became a disaster when the ship refused to move down the slipway. The failed launch attracted international ridicule. Newspapers portrayed Brunel as a reckless dreamer whose ambitions exceeded his abilities. Investors panicked. The stress took a toll on Brunel's health, but he refused to abandon the project. After 3 months of effort, the ship finally entered the water. By then, the financial damage was irreversible. In September 1859, during sea trials, a boiler exploded aboard the Great Eastern, killing 5 crew members and destroying the Grand Saloon. The explosion was caused by a valve left closed after a pressure test, a mistake unrelated to Brunel's design. But the public blamed him anyway. Brunel, already weakened by a stroke suffered days earlier, received news of the explosion on September 15, 1859. He died shortly after, aged 53, exhausted by the strain of defending his creation against relentless criticism. He never saw the Great Eastern fulfill any purpose. The ship, the crowning achievement of his career, became his greatest failure in public perception. The Great Eastern entered service in 1860, but found no viable market. Passenger fares had to be set high to recover construction costs, and few travelers were willing to pay. The opening of the Suez Canal in 1869 drastically cut travel time to Australia using smaller, cheaper ships, eliminating the Great Eastern's advantage. Worse, the ship was too large to pass through the canal, rendering it obsolete for the route it was designed to serve. The Great Eastern's greatest success came not as a passenger liner, but as a cable-laying vessel. Her massive size and stability made her ideal for laying transatlantic telegraph cables, which she did successfully in 1866. But this was a footnote, not vindication. The Great Eastern was scrapped in 1889, 30 years after Brunel's death. During demolition, workers discovered the remains of a riveter sealed inside the double hull during construction, lending credence to rumors that the ship was haunted by mysterious banging sounds. The ship's commercial failure overshadowed its technical achievements. Brunel's double hull design, watertight compartments, and redundant propulsion systems became standard in modern shipbuilding, but he never received credit during his lifetime. The Great Eastern was decades ahead of its time, built for a purpose the world didn't need yet, by a man who refused to accept limitations. Brunel's career was marked by this pattern: visionary designs met with skepticism, ridiculed as impractical or extravagant, then proven correct by time. His broad-gauge railway was technically superior but incompatible with existing networks. His tunnels and bridges seemed recklessly ambitious until they were completed. His ships incorporated innovations that became industry standards, but only after he was gone. Brunel's genius lay not in inventing new principles, but in applying known principles at scales no one else dared attempt. He calculated stress loads, fuel requirements, and material properties with obsessive precision, then built structures that pushed those calculations to their limits. Brunel's working method was relentless. He supervised every detail personally, traveling constantly between construction sites, inspecting work, correcting errors, and driving his teams to meet impossible deadlines. He sketched designs on scraps of paper, calculated in his head, and made decisions on site. He slept little, smoked cigars constantly, and drove himself to exhaustion. His health suffered, but he never slowed down. He believed that engineering was not about caution, but about confidence in one's calculations. If the mathematics were correct, the structure would stand. If the design was sound, the project would succeed. Doubt was irrelevant. By the time of his death in 1859, Brunel had overseen the construction of 25 railway lines, over 100 bridges, 8 pier and dock systems, 3 revolutionary ships, and a prefabricated hospital sent to the Crimea during the war. He had transformed transportation in Britain, making rail travel fast, comfortable, and reliable. His bridges and tunnels stood as monuments to Victorian engineering ambition. Yet his reputation was mixed. Supporters saw him as a visionary. Critics saw him as reckless, wasteful, and stubborn. The failure of the Great Eastern, coming at the end of his life, seemed to confirm the critics' view. History would judge differently. In the decades following Brunel's death, his contributions became clearer. The Great Western Railway remained one of Britain's most important transport arteries. The Clifton Suspension Bridge, completed as his memorial, became an icon. The SS Great Briton, once run aground and abandoned, was salvaged, restored, and recognized as the first modern ship. The Great Eastern, though a commercial failure, laid the transatlantic cable that connected Europe and America, enabling instant communication across the ocean. Brunel's innovations, initially dismissed as extravagant, became the foundation of modern infrastructure. Brunel's legacy is not measured in monuments, though many of his structures still stand, but in the principle that engineering should serve ambition, not limit it. He demonstrated that the greatest obstacles to progress are not technical, but psychological. The refusal to imagine what hasn't been done before. When told that a tunnel couldn't be built, a bridge couldn't span a gorge, or a ship couldn't cross an ocean without sails, Brunel calculated whether it was impossible or merely unprecedented. More often than not, it was merely unprecedented. His refusal to accept limitations expanded the boundaries of what engineering could achieve. Brunel's contemporaries often misunderstood him. They saw his projects as ego-driven spectacles, expensive gambles that risked investors' money for personal glory. But Brunel's motivations were not personal. He believed that infrastructure shaped civilization, that fast, reliable transportation would transform economies, connect communities, and improve lives. His railways made previously distant cities accessible. His ships made international travel practical. His bridges and tunnels eliminated barriers that geography had imposed for centuries. He saw engineering not as a profession, but as a means of reshaping the world. The criticism Brunel faced was often rooted in conservatism. Engineers of his era were trained to build cautiously, using proven methods and conservative safety margins. Brunel pushed those margins to their limits, trusting his calculations to justify risks others wouldn't take. When the box tunnel was proposed, critics predicted it would collapse or suffocate passengers. Brunel calculated the ventilation and structural requirements, then built it. When the Clifton Suspension Bridge was proposed, critics said a single span couldn't support the weight. Brunel calculated the tension in the chains and the strength of the towers, then designed it. His willingness to trust mathematics over intuition set him apart. Brunel's influence extended beyond Britain. Engineers worldwide studied his methods, adapting his designs to their own projects. His use of wrought iron in bridge construction influenced American engineers building suspension bridges in the mid-19th century. His ship designs inspired later generations of naval architects. His railway engineering principles, particularly the emphasis on minimizing gradients, became standard practice. Brunel didn't invent these techniques, but he applied them at scales and in contexts that demonstrated their potential. He showed that engineering could be bold without being reckless, ambitious without being impractical. The Great Eastern's failure obscured an important truth. The ship was technically successful. It sailed reliably, survived storms that would have sunk smaller vessels, and performed exactly as Brunel predicted. Its commercial failure stemmed not from engineering flaws, but from market conditions Brunel couldn't control. The ship was designed for a world that didn't yet exist, a world of mass transatlantic and transoceanic travel. That world would arrive in the late 19th and early 20th centuries, when ships even larger than the Great Eastern carried thousands of passengers across oceans. By then, Brunel's pioneering work was forgotten, his innovations absorbed into standard practice. Brunel's death at 53 robbed Britain of decades of potential contributions. Had he lived longer, he might have applied his talents to emerging technologies like steel construction, electric power, or internal combustion engines. His ability to master new fields, demonstrated by his transition from civil engineering to shipbuilding, suggested he could have excelled in any domain. But his relentless work schedule and chronic health problems, exacerbated by the stress of defending his projects against constant criticism, cut his life short. He worked himself to death, driven by a compulsion to build that consumed him. In 2002, the BBC conducted a public poll to identify the 100 greatest Britons of all time. Isambard Kingdom Brunel ranked second, behind only Winston Churchill. The results surprised historians, who noted that Brunel's public profile had been relatively low compared to politicians, scientists, and artists. But the public remembered him as a symbol of Victorian engineering ambition, a man who built structures that still define Britain's landscape. The Clifton Suspension Bridge, the Thames Tunnel, Paddington Station, the Box Tunnel, and countless other works stand as tangible reminders of his vision. Brunel's story is a reminder that innovation is often punished before it is celebrated. The death ray they demanded never came from Watson Watt. The biplane they trusted couldn't match Mitchell's monoplane, and the cautious engineering they expected couldn't produce Brunel's bridges, railways, and ships. Each of these men faced ridicule, skepticism, and professional attacks because they refused to accept conventional limits. Each trusted their calculations, their measurements, their disciplined analysis of problems, and each changed the world by doing so. Brunel's name endures because his work endures. Every train that crosses the Royal Albert Bridge in Cornwall, every vehicle that passes through the Clifton Suspension Bridge, Every ship built with watertight compartments and double hulls carries the imprint of his engineering philosophy. That audacity, properly calculated, is not recklessness but vision. The megalomaniac they mocked became the engineer who connected the world. The ships, bridges, and railways they called extravagant became the infrastructure of modern civilization. And the man who died exhausted, defending his creations against critics who couldn't comprehend them, became a symbol of what engineering, at its boldest, can achieve.